Hello, my name is Paul Wilson and I am here with my colleague David Clement, and we are the engineers in control. This is the fifth talk in our series Control Systems 101, and in talk number 5 we are going to convert a simple second order electronic circuit into a differential equation. So here's our simple circuit. I'll have a resistor, I'll have an inductance, and I have a capacitor. I have an input voltage and an output voltage. Now the input voltage can be anywhere from DC through to a very high frequency. I'll label my resistor R, I'll label my inductor L, and I'll label my capacitor C, and those will in fact give the values in ohms, henries and microfarads. Now, assuming there is no current taken from the output, the current through each component is identical. We know if the frequency is 0, in other words it's a direct current through here, there won't be any current flow because the impedance of the capacitor will be infinity. And so the current won't flow because the capacitor will just basically block it. If the frequency is extremely high, then the capacitor looks like a short circuit, but the inductor doesn't. The inductor will impede the flow of very high frequencies because the impedance of the inductor is very high. Okay, so if we have a look at the balance equations and using Kirchhoff's voltage law, what we can say is that V in is equal to V1, that's V1 there, plus V2, that's V2 there, plus V3, and that's V3 there. Alright, so using our differential equations that we saw in the chart, what we can say is that V1 is going to be IR by Ohm's law plus L di by dt plus 1 over C integral I dt. We have an integral and a derivative, so what happens, how do we get rid of this, how do we resolve that? Well, we can differentiate. And we end up with this, dVn, in fact we can put that to 0, equals di by dt times R plus L d2I by dt squared plus 1 over C I. So we've differentiated that to give this, and we have a differential equation for our electric circuit. Now this equation that we've got here in fact defines the behaviour of this circuit, and we in fact call that the characteristic equation. And when we move on into transfer functions, we will talk quite a lot about the characteristic equation for the system. But what happens if we want to know what's going on at the output? It starts to get quite messy, in fact. And we need to start just with a bit of electronics, if you're not familiar with it. I'm going to draw what's called a potential divider circuit, a volume control if you like. And the output comes from there. That's V out, and that's V in. That's R1, that's R2, and the equation for V out is If you're familiar with Ohm's law, you should be able to derive that fairly quickly. Now, it may not seem obvious to you, but for our circuit, this one here, then what we get is V out equals V in multiplied by this 1 over C integral I dt over IR plus L di by dt, the characteristic equation here on the bottom line, 1 over C integral I dt. And that is what gives us the output, and this is where it gets really messy. You know, I just falter when I start trying to solve a thing like that. But fortunately, we control engineers have a much better way of doing it, and we convert these into the S domain. And that is what I'm going to start talking about in the next few talks. Thank you very much for listening to talk number 5, and I hope you will join us for talk number 6, when I'm going to do a similar exercise for a mechanical system. The engineers in control are Dr. Paul Wilson and David Clement. You can find out more about us at www.engineersincontrol.com. Unless explicitly stated, all content in this video is original and is copyright 2022 by Dr. Paul Wilson and David Clement. All rights reserved.